So good morning, everyone. Welcome to the Master Thesis Defense of Christopher Cheng. I served as the director of this thesis and also as his thesis advisor, his master's work advisor. My name is Emina Sholyanin, and we have here two committee members, Professor Anand Sarvati and Professor Salim El-Rehab. And Chris has started his master's program last September, so September 2020. Started working a little bit on the problem a few weeks before that, and is now ready to defend his thesis, and he'll be working with us through the end of January. So without further ado, Chris, you're now welcome to share your screen.
Thank you very much. So hello, everyone. Thank you for coming to my thesis defense. If you don't mind, allow me to take a moment to share my screen. You'll see there's like two of me in the meeting right now. That's because I'm going to use the other of me to present, because that has the bigger screen. So maybe the figures and stuff might be easier to see. So, okay. Okay, I see it on that side.
Looks good to me.
Looks good.
Present.
Yeah. Yes.
Okay. Yeah, so I am Christopher Cheng, and I'll be giving my presentation now on my thesis, which is titled "The Effect of Detector Recovery Time on Time-Entanglement QKD Key Rates and an Online Tool for Calculating Such Rates." That's quite a mouthful, so let's take a look at what I'm actually going to be presenting. So here's the table of contents. So section 1, system model. So the structure of this presentation roughly is gonna follow how I've structured my thesis, and I've omitted some things that I thought might be better to just only have in the thesis. So what's over here is first we have the system model, and this means I'll describe how we modeled the QKD, this quantum key distribution that happens from end to end. And so we're modeling what the detectors see, and also how we get the key bits out of what the detector sees. And then we'll go over exactly what is this problem that I was focused on. What was I trying to solve? Which is this effect, which results from the titular detector recovery time. And we'll see how I dealt with that using Markov chain models. And then I'll sort of go over the online tool. So I'll be jumping out of these slides and then actually going into this online tool which uses the methods which I described in the previous section to calculate these key rates. And then at the end is just a collection of some other relevant research work, which I did, but doesn't quite fit, and I would say doesn't quite fit into the main body of the thesis, but it is relevant. So I'll be addressing those ideas at the end of the presentation if we have time. So we move on to section 1, system model, and then here I'll introduce the model of our model of the end-to-end system and explain why we use not just QKD, but more specifically time-entanglement based QKD. And then I'll explain the bit extraction schemes, or I'll use this sort of interchangeably, this term bit extraction scheme with binning schemes. And finally, I'll introduce what this detector recovery time is. Okay, so introduction to system model. So we have a source which generates entangled photons, which are carried along fiber optic cables before reaching the single photon detectors on each side. So in quantum key distribution, what we're doing is establishing secure communications between two parties by sharing qubits or quantum bits between them. And for the rest of the presentation, we'll want to assume two communicating parties who we'll call Alice and Bob. And the idea is that because of the way quantum systems work, it's impossible for an attacker or some eavesdropper of some kind to observe these qubits without modifying the quantum state in some way. And these modifications, these changes can be detected by Alice and Bob. So the matter of, and in a way, the matter of cracking this key from the point of an attacker, it becomes more of a statistical one that's out of your control rather than a computational one that theoretically could be solved with sufficient computational power. So in theory, no amount of computational power would make you more capable of cracking the encryption key shared through QKD than computers today are. So this is what this this step over here does. We have a source which generates these entangled photons. And then in our setup, we use this, what this source is this SPDC crystal. And this enables us to generate the entangled photon pairs because the idea is that we fire a laser into the crystal, and then due to the properties of the crystal, every photon has a chance of spontaneously undergoing parametric down conversion, which is why it's called the SPDC. And that simply means what I said before, which is that we have these singular photons going through the crystal, and then there's some chance that it just spontaneously splits into these entangled pairs. And so in a way, we'll be assuming a noiseless channel, e.g. no photon loss. And so for the most part, we'll be assuming a noiseless channel. And this is because we'll only be analyzing one channel. And the reason why is that downtime is, in a way, its own special kind of error. If you want to put some names to it, downtime could be considered to be what you might call synchronized errors, while other sources of noise like jitter are unsynchronized errors. And that's because in theory, and this is in ideal conditions.
That's a nice way to put it.
Yeah, and the reason why it's called that is because if Alice and Bob both have detectors with the same downtime, then it could be that they still get the same key. So there are no disagreements. But still, because of the downtime, as we'll see, we could end up losing entropy rate because the key isn't as random as it could be. So if you don't address downtime as its own separate thing, if you don't address synchronized errors as their own thing, and if you just try to apply some classical information reconciliation kind of thing, nothing would happen because there wouldn't be any errors to fix. All the bits agree, it's just that the bits might not be maximally random. So to introduce some parameters down here on the bottom half, we have, we'll be assuming that from the point of view of Alice or Bob, that photons will be arriving at our detectors at a rate lambda p with exponential interarrivals, or you could say the number of arrivals you see within a certain amount of time is Poisson. And so if we choose to discretize time in intervals of length tau, we end up with this Bernoulli process with parameter p, where p is given by this formula, which you can derive by using the fact that these arrivals should be Poisson. Okay, so now we're going to start to, so what I just explained was why we use QKD, and then here I'm going to start to talk about why we want to use time entanglement QKD specifically. And that's opposed to other forms of entanglement, which you might want to use in order to extract these key bits. And these entangled pairs, which come out of the SBDC process, they're very highly entangled. So aside from time, you could also use polarization. And you may be asking why we choose to use time entanglement over polarization, which is, at least from how I see it, it seems to be a bit more well known. One reason is that while polarization entanglement can only give us 1 bit of information at most per photon, the number of bits we can get from time entanglement is it's dependent on the time resolution of our detectors. And so this is important because the SBDC effect is fairly rare. Only about 1 in a billion photons actually undergo the SBDC effect. So the number of photons coming our way, going to the detectors that Alex and Bob have is limited. So if you see here, the polarization-based QKD, or rather an upper bound on that rate, would just be lambda p, because which is the rate that photons arrive at our detectors, because you get at most 1 bit per photon. So the amount that the rate at which you get bits would just be the rate at which you get photons. And then if lambda p is low, then your key rate is going to be upper bounded by that low lambda value, and there's not much you can do about it at that point. But on the other hand, the bits of entropy we can extract from time-based QKD, that depends on the probability that a bin is occupied by at least 1 photon. And so that's that depends on that Bernoulli process that we were talking about before. And that's what this the rate upper bound is, what we see over here. That's the expression on the bottom right. And we have this H function, which is the binary entropy function, and tau, which we described earlier, which you could also call the bin width. And then the idea is that if you could arbitrarily adjust tau, so see how tau is just in the denominator here. So if you could decrease tau arbitrarily, you could just make this bound as high as you want. Just to see a visual comparison, here's how R sub p, which is the key rate, the maximum key rate given by polarization entanglement, compares to R sub TOA, where TOA means time of arrival. So that's going to be the maximum key rate which you get by using time entanglement. So here in this plot to the right, the x-axis represents lambda p, and then we can see that there is a point, a threshold, where R sub p exceeds R sub TOA, and will continue to for all larger values of lambda p. But the thing is that this threshold can be moved arbitrarily, like I said before, as if you just make tau sufficiently small, you can just make this threshold, which I sort of highlighted using this black vertical line. You can just push it like to the right as far as you want. And to put some like real numbers to this, these days, tau seems to be pretty small because, or at least the minimum possible, theoretical minimum possible tau is pretty small because, for example, the detectors that were used by a team at UCLA that was collaborating with us, the detectors they use have 4 picosecond resolution. So I would say that's pretty small. And then
you need tau to be very small in general, otherwise the Posaunus, I mean, your Bernoulli assumption doesn't hold, right? Unless tau is very small.
It would, because
I mean, like there's a problem with making, I mean, there's a problem with tau being too large. If tau is too large, you could have multiple arrivals in one bin, and then your lambda.
Oh, you always could. That's actually this form. If I did it correctly, then this formula should take care of that. This should this is just the probability. So see here how I'm calling it the occupancy probability of a bin. So this is just the probability that there's a non-zero amount of photons inside the bin. So if there's 1 or 2 or 3, and so on, this should be the probability of that happening.
Okay. Sorry. Okay. Thanks.
Okay. So let's see, where was I? Okay, so over here, time entanglement key rate security. So maybe the rate of time entanglement is potentially better than the rate from polarization entanglement, but one may still have concerns about the security of the system, because we were talking about earlier how theoretically Alice and Bob could detect whether there were any eavesdroppers, or maybe there's just too much noise and you don't want to use this channel because there's too much noise. Thankfully, we can we have the same, if not better, levels of security compared to polarization entanglement, thanks to these Franzen interferometers. And that's because these Franzen interferometers, they expose us to this quantum, they expose to us this quantum state here, where instead of the vertical and horizontal axes of polarization, we instead have these short and long paths in the interferometer, as you see below. So if you just went straight from the source to the far right detector, that would be considered the short path. But then if you got redirected by this beam splitter over here, and then went over here through the phase changer, that would be considered the long path. And the thing is, by using, adjusting how this phase is shifted by this phase shifter over here, you can choose at which angle to measure this value at. So that's analogous to like how in polarization entanglement, you can physically change the angle of the filter, and then in a way you measure the quantum state at angles which are different than just the basis values of just exactly horizontal or exactly vertical. And then because of that, we are now able to once again perform protocols such as BB84 and maybe play the CH-SH game, which are things that would allow us to determine whether it is messing with our channel. For instance, again, if there's an eavesdropper in the system. So because of this, so this is the security argument. So because of this, together with the rate comparison from earlier, we want to claim that overall time entanglement seems to be just a superior alternative to polarization entanglement, which is why we want to focus on time entanglement right now. And so now we're using time entanglement, but then how do we actually get these bits? So we've been talking about the bit and information rates so far, but what are the actual literal bits? So we have these photons arriving at the detector, and we're discretizing time into these bins. And then so on the bottom here is sort of a visualization of what this might look like. And these bins are either occupied if at least one photon was detected within it, or unoccupied otherwise. And in this visualization, this figure down here, the occupied bins are represented by if you have a blue dot inside it. So as mentioned before, whether we get these blue dots inside these bins, it's determined by this Bernoulli process. And so we can interpret this as sort of like a bit stream. So because we have this Bernoulli process, so we get either 1 or 0 with some probability. And now we want to extract maximally random key bits by using this bit stream. Then, but in general, you're not going to be using a scheme that sort of achieves this bound with equality for various reasons. And instead, you'll be using something for instance, like the quite popular pulse position modulation, or PPM. And real quickly, the idea is that we group the bins into frames of size n. So if you look at this figure below again, you'll see that if you look at these lines over here, you can see that they kind of split up this sequence into groups of, you would say, n equals 8. So there's 1, 2, 3, 4, 5, 6, 7, 8 bins in each frame is what you would call it. And so in order to use PPM, here, what we do is see whether the frame is 1 hot encoded. And if it is, you decode it, and those are the bits you get. Otherwise, you get no bits. So in this case, you can see that in this leftmost bin over here, that is 1 hot encoded. And in fact, the occupied bin is in the very first position. So you're just going to get 3 bits here, log 2, 8. You're going to get 3 bits here, which are just 0, 0, 0, because this occupied bin is in position 0. And then for the other ones, those are not 1 hot encodings. So you're just going to get nothing from these. And so that's sort of why you might say that PPM is not it's not something that will achieve this bound with equality. And we'll see that later also as well with some plots. So you can see here the key rate that you get when you use PPM. So just real quickly, how you derive this is that the probability that you get a 1 hot encoding is n times p times 1 minus p to the power of n minus 1. And then so that's the probability that you get a frame that will be accepted by PPM. And then the number of bits you get is log 2n. But then that's going to be the bits per frame. And here we're looking at bits per bin. So we just divide by the number of bins, which is n. And so we just get log 2n times p times 1 minus p to the power of n minus 1. And so this is what it looks like when you plot things out, where the x-axis is p, where p is again given by this formula below. And yeah, this is the same formula as the one a few slides ago. And you also might notice that in the title of the thesis, I used the term recovery time, but here in this slide title, I'm also using I'm saying downtime, and that's because the terms recovery time and downtime seem to be interchangeable in the literature that I've seen, at least. So I'll be using them interchangeably here as well. Hopefully that doesn't make things too confusing. So here we have PPM, but there are also other binning schemes that we could try to use, which were not designed by me, but by someone else who worked on the project. I don't know if any of you know of someone who goes by the name Naveed. But anyway, he's the one who came up with those. And I'll be describing those later when I talk about the online tool I put together for calculating these key rates and entropy rates. Because that's where I'll be, where I actually used them. For most examples I'll be showing, if I ever don't specify what I'm using, you can just assume that it's PPM. And one important thing to note here is that these binning schemes, so all of the ones that Naveed designed and also PPM as I've described it here, all these binning schemes have something in common, and that's that they break the bit stream into chunks of n bits and then process the n bits, these frames of size n, all separately. And it's this structure which is going to play a huge role in the way I address the effect of non-zero downtime later on. So what is this detector recovery time? So downtime is an intrinsic property of a detector and is the period of time after a photon detection during which no other photons can be detected. And so we're gonna, from now on, we're going to be denoting this as a parameter d, where D is in units of bin widths. So whatever tau is, if D is equal to 1, you can assume that the downtime is equal to tau. And what this downtime does is that we had these bins, which used to be uncorrelated. We used to have this Bernoulli process, right? But now there's a possibility that there may be like some correlations of some kind, because for instance, if one bin is occupied, that may decrease the probability that the next bin is occupied. And as you see down over here, so instead of blue dots, we have orange dots instead, but it's the same thing. And you can see here, this is the example of D equals 10. So if you didn't have any downtime, this first frame would be rejected under ppm, because there's 2 occupied bins. So you wouldn't get any frames here, you wouldn't get any frames. So for now, just ignore the downtime. So you wouldn't get any frames here. You wouldn't get any bits here. You would get some bits here, and you get some bits here. But then once we do consider downtime, you can see that suddenly this first frame, which wasn't valid before because there wasn't a valid one-hot encoding, well, the downtime from that first occupied bin is covering up the occupied bin that comes after. And so now you only see this occupied bin, and now it looks like you have a proper one-hot encoding. And so you would actually get some bits out of this. Over here, you can see that in the rightmost frame, we had a proper one-hot encoding, but because of the occupied bin in the last frame, this rightmost frame you no longer see this occupied bin, and so you don't get any bits from there. So this downtime has the ability to potentially make frames which originally didn't give bits give bits now, and then make it so that frames which used to give bits now no longer give bits. So and in the abstract of my thesis, I kind of mentioned this problem of what if this changes whether the rate from time entanglement really is better than polarization entanglement. And that's actually something I'm going to end up going over a little bit in further research. For now, we're going to see why this affects this way that downtime changes whether a frame is accepted or not, why this may lead to some unintuitive effects, and why this may and how this may like change the entropy rate of our key, which theoretically used to be if there was 0 downtime, which theoretically used to be perfectly random. So that means we're moving on to section 2, problem formulation and solution. And so we're going to be going over what downtime does to our key rates and how we calculate these modified key rates. So to sort of visually show what's going on, so if we look over here in this plot, we have x-axis of p. So the x-axis represents p, and the y-axis represents r sub TOA. And you can see here as p increases, r sub TOA appears to it seems to rise up and approach a constant value. So if you didn't know better, you might look at this and then conclude that maybe the best value of p for us would be as close to 1 as possible, and that would be the same thing as saying you want lambda p to be as high as possible. But then look at this. So what I claim is that this is actually the true key rate, or you might want to call it the entropy rate instead. So if you had really chosen a value close to p, then your r sub TOA value, according to this plot, would now be also close to 0. But then if this was the true key rate, then what was this? What were you looking at before? So what the calculations didn't account for in this plot over here is the downtime. And this plot over here, on the other hand, does account for the downtime. And the question is, how exactly are we going from this to this? what are the calculations that I did? So in order to sort of start to get an intuition for how this key rate can actually drop down to this value when you do consider downtime, this perceived key rate, we can consider this extreme case of n equals 2, d equals 1, and p equals 1. So that means we have a frame size of 2 bins. Each downtime lasts for 1 bin width, and the probability that a bin is occupied is 1, which means that all bins should be occupied. But since downtime is d equals 1, the detector will see every other bin as being unoccupied, and so the bit stream we'll get is just something like 10, 10, 10, 10, and so on. And what's important is that since n equals 2, this will always give us valid 1-hot encodings for each frame. And so each frame is just going to be all 1 zeros or all 0 1s. And if we apply ppm to extract the key bits, we're just going to get key bits that are all zeros or all ones, and that's not going to be much of an encryption key. So even though we're getting literal bits, we're getting no information at all. We're getting no entropy at all because the bit sequence is deterministic. So to start addressing these effects more analytically, we want to start by modeling the detector using this Markov chain down here. And the idea is that so over here, state 0 represents the default state of the detector. And then the idea is that with probability 1, we go on this train of states, which starts at 1 and then ends at state D. So we have D states where the detector isn't going to be able to detect any more photons. So we have 0 with probability P, you see a photon, and then 1, 2, however many to get to D, and only then do you go back to state 0 where you can once again have the possibility with probability P of seeing a photon. And then the Markov chain entropy that we get from this will help us get our upper bound, which is going to be h of P over 1 plus P times D. So that's the amount of information we get per bin. And so in order to get the rate of bits per bin, it's just going to be that divided by tau. So that's why our sub TOA is now the new upper bound on this key rate is going to be h of P over tau times 1 plus P times D. And that's so what we're seeing over here on the right is tau times that. So we're gonna be looking at the entropy, the amount of bits that we get per bin. And here you can see what you're looking at here is that that curve, that bound for various values of D. So if D equals 0, you're just going to end up getting the binary entropy function on its own. So that's this largest curve over here. But then you change D to 1, and then you get this lower curve, and then D equals 2, this lower curve. So as D increases, your entropy, the upper bound on the entropy rate you can get does in fact decrease. And then here, yep.
I guess. Do you have I mean, maybe you didn't do this calculation, so you don't know. How fast is the peak decaying as a function of P?
How fast is the peak?
So if you go back to the previous, so as you increase as a function of D, right?
Okay.
As you increase D, you're pulling the peak. The peak is sinking down.
Right.
And I just wasn't sure. Like, I'm just curious. I don't know why you would have any reason to do this calculation. So it's more like
I indeed didn't do any calculations for that. But if you just I only showed a few values of usage equals 0, 1, 2, 3, 4, 5. But on my own, I did look at more values of D. And it just seems through visual inspection that this peak is just going to asymptotically approach 0.
Okay. Yeah. I mean, that makes sense. I just wasn't sure how fast, but cool. Anyway, thanks.
Okay. So over here, we're just going to take a look at some of these formulas that we've had so far to calculate the key rate. So you can see over here, this red one on the bottom is the rate for ppm that we saw earlier. You can see that it's quite a bit, quite far away from the upper bound. And that will make it so that we have to complicate things, actually complicate things a bit in order to calculate the true key rate. So we have this this red curve, which is ppm, and then we have this black curve, which is just what we saw earlier, tau times r sub TOA when you do consider d, and I don't remember what the value for d is. It looks like it's probably just d equals 1. And then here is just the, this would be the case of the green curve would just be the case of d equals 0. So that's just going to be the binary entropy function on its own. So what we have here is an upper bound on the entropy rate for downtime 0, so no downtime. And then we also have a formula for the upper bound for non-zero downtime. And then here we have a formula for the key rate that we get through ppm. So where do we get the curve for the key rate of ppm when d is non-zero? And then for that, we're going to have to use, in this context, what I call Markov chain methods for calculating these key rates. And we have two, which are the basic Markov chain method and reduced Markov chain method. So I'll be calling those BMCM and RMCM. And these are methods which take advantage of that behavior of the binning schemes that I described earlier, the fact that we split the bit stream into frames of n bits. And so it uses that structure to generate Markov chains that model what the detector sees. So given these parameters n, d, and p, which again are the frame size, the downtime, and the bin occupancy probability, we just need these 3 parameters and it'll generate. So this is not just any one Markov chain, it's a method which you use to generate Markov chains using these parameters. And then these two methods, BMCM and RMCM, they result in what you might want to call an input Markov chain, or IMC, because it sort of describes what the detector receives as input. So at this point, you're still not really, you don't have to consider what binning scheme you're using. But then if you want to get the entropy rate, so if you want to go from this to this, then you're going to have to use, you're going to actually have to go one step further and use something called the OMC, or output Markov chain, which you actually get by putting in the input Markov chain and also the scheme that you're using as an input. So, and that's because we need, because the output Markov chain now describes what we see after the binning scheme is applied. So first we introduce the base. I know this is a little bit late, but have you been seeing this thing the whole time? There's a thing. Oh, never mind. I can see it on my other. Okay, because there was a little label covering my screen. I was saying set up professional audio and audio settings, but I don't think you see it in the presentation. Okay. So first okay. So basic Markov chain method, or BMCM. And the idea is that we consider all possible frames where whether a frame is possible depends on the downtime. So in the case of downtime equals 0, you would get the worst case, which is 2 to the power of n states. Otherwise, you can use this recursive formula down here, which will give you the number of states. And then the idea is that once you have these frames, each frame is represented by a single state, and then you can connect these states with some transition probabilities, which depend on the frame configuration, which depend on the frame that each state represents. And in general, the number of states increases exponentially as n increases. So it's just scaled differently based on what downtime we have. And as we'll see, I tried to address that with the RMCM. And then in the end, something I think is pretty interesting came out of that. So if you look at this plot over here, you can see sort of how the number of states increases as you change D and N. And you'll see here, so in this over here on the far left is D equals 0. So you can see here, when n equals 29 or so, why does it seem like the number of states is like 30? And that's because this plot is at the y-axis of this plot. It's actually a log plot. So when you see over here that it's like about 30 or so, this number of states is actually 2 to the power of 30. So we're getting quite a lot of number of states. But then as you can see, the number of states does decrease as D increases. So you can see the far left is D equals 0. And as you move to the right, this curve does go down. And then, so earlier, just earlier, I was saying that we connect these states with transition probabilities depending on the frame configuration that each frame represents. And what this, to show what this means, I'm going to be going through this sort of a toy example. So here we have a case of n equals 2 and D equals 1. And then notice how the 1, 1 state, so we have these states here, these 3 states, 0, 0, 0, 1, and 1, 0. But we don't have a 1, 1 state because it's impossible because D equals 1. So once we see an occupied bin, the next one is implied to be 0. And then here we see some P's and Q's. P is the bin occupancy probability again, and Q is just going to be 1 minus P. So over here we see 0, 0, and then it transitions to itself with probability Q squared, because that's the probability that we see another unoccupied bin, and then get another unoccupied bin after we see 0, 0. And then over here, you can see this is the probability, PQ would be the probability of seeing a 0, 1 after a 0, 0, because you need the Q tells you that you're going to see this 0 over here, and then the P tells you that you're going to see this 1 over here. But then how come if you're going from 0 to 0, 0, 0 to 1, 0 instead of 0, 1, the probability is now not PQ, but just P? Well, that's because in this first bin here, you have an occupied bin. So that happens with probability P. But then the unoccupied bin right after it is implied, it's guaranteed, because of the downtime of D equals 1. And so you don't need to have a P times Q. It's instead P times 1, because P times the probability that you'll get a unoccupied bin right afterwards, which is going to be now 1 in this case. And you follow sort of the same logic going between all of the states, which is where you get these transition probabilities. And then now we have this reduced Markov chain method, which is something I designed in order to address the fact that this BMCM has sort of like exponential growth as the number of states, exponential growth in the number of states as n increases. So over here, we try to reduce this to polynomial growth in the number of states as n increases. And we do this by relying on something I call the combination condition, which basically allows you, so as long as we have these sets of Markov chain states, if we can find A, M, and B that fulfill these conditions, then you could just take all the states in M and sort of combine them all into one state. And then so when you so that when you use the Markov chain to do these key rate calculations, you don't have to use as many states, and you sort of save on computation time. And the idea is that instead of generating all these states, so all like potentially to the power of n states, and then having to find A, M, and B, this reduced Markov chain method instead, in a way, we generate the states we generate are combined already. And so we can skip having to even have this like exponential number of states in the memory. So there was the issue of having this exponential number of states in memory, and there's also the issue of having to use this Markov chain, which has an exponential number of states in it, to calculate some stationary probability. And
I'm a little confused here. Just I think about what A, M, and B are.
So if we have,
can you only go from A to M and M to B? Can you go from A to B? Are you clumping all the M's together, all the A's and all the B's together, so you end up with
no, the A's and B's stay, but the M, the set of states of M, that all the states there can be combined together.
So this will only help you if M is like, if A and B are very small compared, and M is like most of the states or something.
Something like that. I mean, there isn't really a limit on how large the sets A and B can be also. But like you said, the main concern is like if M is really large, then it would be really helpful if we could just combine them all together into one state.
Okay, because you mentioned polynomial growth, so this is like, I'm just trying to get a sense of how big these sets are. But I guess you'll say in the next slide. I just got the generality was confusing to me. Sorry.
Okay.
I have another question that you may have mentioned it, but I missed it. So, I mean, here, what is the kind of the sufficient statistic that you're interested in? Are you interested in the total number of photons, or are you actually interested in which photon is, or the state of each bin? I mean, in the end.
Yeah, what we're looking at to actually extract the key bits is the occupancy of a bin. So when we discretize time into these bins, we end up with this Bernoulli process, and this Bernoulli process is what we're sampling from in order to get our bits. At least the bits that represent what the detector sees.
So in the end, you're interested in knowing the occupancy of each bin.
Yes.
But then in this case, I don't see any way of reducing the complexity of the Markov chain.
I mean, let's like A and B are polynomial and N, and then M is like, exponential minus polynomial.
I mean, you could take a look at it if, because in the, I didn't add it in this thesis, but in the, I didn't add it in these slides, but in the thesis, you should be able to find the part where I sort of, where I have the formula that tells you how many states are in the Markov chain. And if you look at that, if you look at those formulas, I looked at them and it seemed like they should be polynomial. So
let's just see if maybe something more fundamental is not understood. So so what introduces the memory and hence the Markov chain is the detector downtime. Otherwise, would be just Bernoulli trials. Now, if we don't have this framing, then that Markov chain is a very simple one that Chris showed much earlier, and the entropy of that is clear. Now with framing, you have to look into many states, because that also introduces states, not only the state of the detector, but also the state of the frame. And then that is the number of states that Chris is trying to reduce. So I'm just not sure if that basic thing was understood, but maybe it is. So I'm sorry.
The frame size is n, right?
Mhm.
So, I mean, it's 2 to the n. There's like 2 to the n possible frame states, right?
That's in the case of that's the worst. That would be the worst case I mentioned before with
Yeah, right. The worst case,
You
right?
have d equals 0.
Equals 0, and so then, but still, even if d is so if d is not 0, but you'll still have a very large number of states.
You'll still have exponential growth as long as you're using BMCM.
Yeah,
Right.
so maybe exactly that's the
Right,
slide.
so that part I
the toy
understand.
example is good.
Right, that part I
Okay.
understand. And I understand the idea that you want to take some states, maybe you can group some states together and then you can get a better, more tractable, chain, which is smaller, has a smaller state space so that you can then like analyze or simulate or something. But it seems hard. I guess maybe you're going to show me explicitly.
Well, yeah, I'm gonna.
It just seems very like a very surprising thing to be able to do, to essentially take the vast majority of this exponential number of states and clump them into one state m, right?
Yeah, so I think that's what the next step, the next slide might
Maybe
go over.
that's what I'm like, yeah, it was just okay.
Yeah, so how do we create these states which are already combined? So the idea is that we have these 3 numbers which define all of these m sets. And these 3 numbers are downtime into a frame, downtime out of a frame, and a third number, which determines how many occupancies we find in the remaining space. So the reason why I say that it's polynomial growth instead of exponential growth is that the combination of possible ways we can have downtime in and downtime out is not going to be that's not exponential, but the ways you can arrange occupancies within the remaining space, if you're not so clear about it, I'll explain what remaining space means later. The amount of ways you can arrange the number the occupancies inside the possible occupancies inside the remaining space, that is exponential, but we're combining all of those together. And so we're sort of like, we're sort of smoothing over this. We're combining we're reducing this exponential behavior to just be, the behavior of how many d sub i's and d sub o's there are.
So this is okay. This is okay if d is like not the same scale as n.
Right. That's actually something I'm going to address briefly in further research.
Okay.
So
also, are these two, I mean, in the end, are you losing anything by kind of using this, let's say, simplified Markov chain?
no, and if you if you use the theoretically you should be able to get the same thing. And when I've looked at the plots I generate by using these methods, they do at least appear to give the same thing. And the main difference is computational complexity due to the number of states. So
could one think of that using the Markov chain where the states are the state of each, the occupancy of each bin is not the right Markov chain? You're kind of over parameterizing it, to use a machine learning term. Because sometimes, right, it could be like you're just interested in the number of photons, the number of balls in these bins. So it could be, instead of, I mean, it depends what in the end you're interested in. You could just model the state as the number of occupied bins, for instance.
because
it's ppm, only one bin is occupied.
Yeah, so the number
in
of
the
them.
frame. So
Okay.
sorry,
Only one per frame.
only one bin per frame.
Okay. No, I'm asking more a conceptual question. Like it could be that the original.
But you gave a concrete example. That's what I was answering.
Yeah. So what I'm trying to understand is this kind of an approximation of the Markov chain, or more like this is really.
No, this should model it completely. The RMCM and BMCM, like the results you get from those, should be exactly the same.
Okay.
Okay, so so I'm gonna let us consider here this case of downtime into a frame 2, so that's d sub I equals 2, and downtime out of a frame equals 1, so that's d sub O equals 1. Now in this scenario, d equals 2, so downtime spans 2 bin widths. So if we have a downtime of 2 into the frame, well, we know that these 2 bins over here on the left are going to be detected as unoccupied. So these are already just by saying DI and DO, by defining these numbers here, we know that these are already going to be, these are like predefined. And then the downtime out of the frame is 1, and that too also implies these 2 bins over here, because we need this occupied bin in order to put the one downtime here, and then because d equals 2, we have one more downtime here, and that results in the downtime out of the frame of 1. And you'll notice here that you can sort of make this easier to think of by considering symbols A and symbols B. So symbol B is just going to be a single unoccupied bin, and symbol A is going to be an occupied bin followed by D, unoccupied bin. So you can see here, that's what you're seeing over here. So downtime n equals 2, and so we put symbol A over here so that we have downtime n equals 2, and then we have downtime out equals 1, and so we put a symbol A over here so that downtime equals 1. And then now we have this remaining space of 4 bins where we still like have a little bit of freedom to like choose what goes into there. And that's where that third number comes in, which I denote. I don't know if I use it anywhere in these slides, but it's called, oh, I did mention over here, which I call n sub A, because it's the number of symbol A that we'll see inside this remaining space here. So for example, in the scenario above, there are 2 ways. So there are 2 possibilities here for n sub A, which is just 0 and also 1. So in the case of n sub A equals 0, well, that's just we're just going to get this bottom frame down here, 0, 0, 0, 0, 0, 0, 1, 0. So that just means that, so whenever you have 0 of symbol A, and then you just fill in the remaining space with symbol B. But then for the case of n sub A, you have 2 possible ways, because you could put the symbol A starting into the space starting here, or you could put the symbol A into the remaining space starting here, and it'll still fit, and then you'll just have to put the symbol B over here. So that's where we get these 2 ways, this 0, 0, 1, 0, 0, 0, 1, 0, and also a 0, 0, 1, 0, and so on. So we have these 2 states, and then the important part is that these downtime ins and these 3 numbers, downtime in, downtime out, and n sub A, these tell you how many occupied bins are inside the frames represented by that state. So that's why we still had to choose some sort of n sub A, because we could have 1, which would mean that there are 2 occupied bins. So you can see that there's 2 occupied bins here and 2 occupied bins here. Or you could have 0 of symbol A in the remaining space. So you only have this 1 occupied bin, which is implied by the D sub O. And so it's this remaining space inside here, which I claim has the it has all of the exponential information in it. You can imagine a case where n was like larger than 8. Like say n is just, I don't think I have to put an exact number to it. Just assume that n is like a lot larger, but we still have the same d sub I and d sub O. And so these boundaries are still going to be the same. We're going to have 2 unoccupied bins here, and then all the way at the end, we're going to have an occupied bin followed by an unoccupied bin. And then we're going to have like a bunch of space in the middle. And then that's space where we can like sort of put symbol A into. So if we said again, like n sub A equals 1, then there's lots of ways that you can put in the case of any n sub A equals 1, you would just put it like sequentially. So symbol A over here, and symbol A over here, symbol A over here, and so on. And all the idea is that all of these would be represented by the same state. And to see why we might want to do this, we can take a look at this other toy example for RMCM. And you might notice right away that there are more states than in the case for BMCM. So in BMCM, there were 3 states. Here, there are actually 5 states. And the reason for that is because when we're using, when we're creating the states in this way, we sort of, the frame now no longer just represents what we see, but also the state of like the state of the detector is also considered along with what we see in the frame. So for instance, if we have a frame 0, 0, 0, 0, it could be that all of those are just unoccupied bins because there were no photons inside that frame. But it could be that we saw 0, 0, 0, 0 because there was a single downtime leaking into that frame, and then the remaining 3 bins were just normally unoccupied. Or there could be 2 downtimes leaking into the frame, and then the remaining 2 frames were normally unoccupied, and so on. So each of these scenarios is actually represented by a separate state in this case. And so we have, that's what leads to some states which appear to be repeats of each other. And so you can see like some triplets inside the state that's supposed to represent D sub I and sub A and D sub O. And then you'll notice that in these transitions, I didn't like put any probabilities next to them, but that's because, so as I mentioned before, this is what the combination condition is for, that all the transitions into a particular state. So these are, you can think of all of these as combined as these M sets that are already combined. And the property of this M set is that all non-zero transitions into the state are the same. And I put that transition probability and I've chosen to put that transition probability inside the state, so like it's not like as cluttered. So all of these arrows that you see going into this state here, all of them are going to be P times 1 minus P. All of the ones that go into this one are P, and so on. But then even though I wanted to design RMCM to sort of like be to be better than BMCM, but instead of that, it turns out it's better to think of them as complements, because it turns out while the number of states for the BMCM decreases as D increases, the number of states for the RMCM increases as D increases. So the 2 methods actually end up complementing each other pretty well. And you can see here, this is the minimum of the 2. So if you have we have this over here, so this is BMCM, and we have this over here. which is RMCM. And you can see here, so the, let's see. Yeah, so the range of values you look at is pretty much the same over here. It's not pretty much the same. It should be exactly the same. It's just that I made these plots as Excel, and I guess it just didn't want to show the far one. So here you can see that the number of states in the BMCM goes all the way up to 2 to the power of, like, it should be over 2 to the power of 30, because there's actually, here's 2 to the power of 30, and it actually goes a little bit above that. Here you can see here, I don't know if you can see it because it's a little bit blurry even on my screen. So I don't know if you can see it, but here, the maximum, the largest number here is, this is not a log plot. So this is the actual number of states you get. The largest number you see here in the same range as we had over here. The largest number is somewhere between 500 and 600. So it is reduced, at least in a way. But then you get the most advantage by actually combining them in the way that I just said. So by just taking the minimum of these two. So if you take two, if you take this and you take this and you find the minimum, you get this, and you can see this ridge over here, and that's where the boundary is. So you can see over here where we have this like little on the left side of the boundary, that's where RMCM is. That's where RMCM has the fewer number of states, and then here is like that's where D equals 0. So that's where BMCM would have that like super large number of states. But then as D increases, the number of states in the RMCM starts to increase, but the number of states in the BMCM decreases. And so you can see where that where the number of states in the BMCM goes below the number of states in the RMCM over here in this ridge. And I didn't like check this too rigorously, but just by looking at this plot, and also I looked at the underlying numbers, which I used to make this plot. It seems like the boundary happens at like at n equals d over 2. So it's really it's kind of it would be interesting if the boundary between these two vastly different methods is determined by such a simple relationship. So as I explained before, these two methods, so if you use this hybrid method, what you would end up with is what you might call an IMC, an input Markov chain. And then, but we still need the output Markov chain. And because this is what it turns out this is what we're going to need in order to get the entropy rate of the key. Yeah, so with either the IMC or the OMC, so pretty much by with the IMC already, you could get this already. But as I said before, this is actually not the full picture. This will give you the rate of literal bits, but it doesn't tell you how it doesn't tell you anything about the entropy of the bits that you're getting. If you want to, if you try to find the entropy rate by calculating the Markov chain entropy of the IMC, you would just end up getting this. You would end up getting this rate over here. So if you found the Markov chain entropy of the IMC, you would end up getting h of p over 1 plus p times d, and so that's why you'd get this h of p over tau times 1 plus pd as the upper bound for r sub TOA again. So by finding this OMC, you get this value, which I call H sub ratio, because that's the ratio between the literal key rate and the entropy rate. So if you take a look at this plot over here, you can see this red curve over here is what we had over, is like what we had over here. But now we can find the green curve, which is H sub ratio. And if we multiply this value, the values from the green curve with the values from the red curve, then you can get the values from the purple curve, and that I claim is the actual entropy that we're the actual entropy rate that we're getting out of this system, given certain parameters. And on a high level, that's pretty much the end of that. So just as a quick review, where we went from we could be given N, D, and P as parameters, along with the bidding scheme being used, and from those values we can calculate what the entropy rate should be, and so what our, you could say, the truer secure key rate is, or at least a much tighter upper bound on that rate. And then so I'll shortly be presenting about the online tool, which uses the methods I described just now in order to calculate these key rates. But if you remember, I mentioned that there were binning schemes besides ppm, and these binning schemes are going to be making an appearance now. So I'm going to explain them real quickly. And we have 4 schemes to go over. The first one is simple binning. So this just means that we have, it's almost the same as ppm, but
okay, so Chris, you're running out of time, so we have to make some decision what we want to do. So I suggest
okay, so I'll just show the tool right now.
Yeah.
I'll show the tool. I'll put the link in the chat if I can. Let's see, how do I do this? Chat.
You chose a dark mode color scheme.
Yes, I have, but if you want, you can actually change it to light.
Oh, wow.
It's really a tool, so click on this link. It's fun.
This link, if I could find it, find a way to post it.
So if you put a mouse on the screen, the chat will appear between.
It's on the bottom. Okay.
Yeah.
Here we go. Okay,
So
there's
you wrote this. You wrote this tool.
Yes.
Yes.
Oh, nice.
It's posted on GitHub pages.
So that's why it got into the title of his thesis. It's really a piece of work.
Yeah, so there was like, it's sort of like the 2 halves. Like I have the theoretical mathematical, like the Markov chain stuff, and then here it is like actually implemented. At least a good part of it is implemented. So we have R that in this website, I called it the naive key rate. So that's what we would see if we only looked at the, that would be the, that would result in that curve where it seems like the closer you get to P, the more key rate you get. Here, this is just what you get because D is 0 by default. So I guess let's not look at the other binning schemes. So let's only consider simple binning. So there are a couple things you can do. You can change the frame size, recovery time, and then you can change the probability of bin occupancy. So this would be the value of lowercase p that we were talking about before. And you can, the reason why I allow you to change this, even though it's supposed to be changing along the x-axis, is because you can change what the x-axis is. So you can set this to D. 0, well, right now it goes from 0 to 1, so not much changes, but you can go from, I don't know, 0 to 10. It still seems like not much. Oh, that's because P is low, but if you increase it, you can see that it changes. It might be a little hard to see because it's blue and we're on a dark scheme, so now it should be easier to see. So this is what you can get if you plot against the downtime. Let's go back to P for now.
This is very cool.
And then change the rate back, change the range back to, or the domain back to 1, 0 to 1. And then one thing I wanted to show is the entropy. And so right now, you might notice that this is like sort of it's noisy. The signal is the curve is noisy because right now we've been using an empirical simulation type. So I'm actually simulating this Bernoulli process and then simulating what the detector is going to see. And then I'm getting the numbers out of that instead of using this Markov chain method. So you can see when D is equal to 0, when recovery time is equal to 0, the bit entropy, the entropy should just, or as I called it in the slides, H sub ratio should just be 1. But if you increase the recovery time, it should go down. But then here's also some part of the motivation of why I developed these Markov chain methods, because you can see on the far end over here, it's moving kind of slowly. And that's because there are so few bits being generated out here that they're, yeah, that's it. There are so few bits being generated out over here. And so the plot empirically calculated entropy over here is very, very slow to move. But if you use, let's see, so that was 8 equals 1, 1. And we switch it to analytical. You can see that this is supposed to be the actual entropy rate. So if you could run this forever, then theoretically, this empirical curve would rise all the way up here. It's a little bit hard to see. Let's choose a darker color again. Let's see. So we get this, and then to show that it's not just always going to be completely different, let's choose a different value of D. So let's go for, I think 2 already starts to, if 2 already starts to be fast enough to like sort of show, does it? Let's see. This is, okay. Now that's still doesn't really quite go up fast enough. Let's just go all the way to 7. That's what 7 is going to look like. And then you can see they overlap pretty much perfectly, which is exactly what I like to see. So I do have to say that this was designed mostly with simple bidding in mind. So, in other words, mostly PPM. So if you use other bidding schemes, it might very well bug out and give you results that don't really make sense. For instance, if we go straight to adaptive bidding here, oh, well, that's the empirical one. If you go to adaptive bidding over here, well, it looks like it's fine now, but if you turn the recovery time back down to 0, you actually get values above 1, which should be impossible. So that is something I still have to iron out. And so there's that, the rate calculation and the entropy calculation. And then let's see, if we go quickly back to simple bidding, you can see that you can also just have the estimated, okay, I forgot a minus sign somewhere. But theoretically, you can get this, you multiply it with this, and then you would get the actual the final estimated key rate. And those are pretty much the most important parts. So let's just continue with this for now. So I was going to explain the bidding schemes, but now I have this. Okay, so now let's try to quickly go over this further research. So applicability of the model. So just as before, we were always assuming that the photons arrive at the detector with exponentially distributed inter-arrival times. And also because of the downtime, it's not just exponential, but a shifted exponential distribution. But when we look at so I mentioned earlier that we have a team from UCLA who was collaborating with us, and they have some experimental data that they were kind enough to share with us. And by analyzing that data, what do we see? Is it actually a shifted exponential distribution? So that's what this histogram over here shows. And you can see that we have this red curve here, which is an exponential fit. And you may say, wow, that looks like a pretty good fit. So the model is correct, right? But actually not quite, because in order to get this fit, we actually had to do something, which is omit all inter-arrivals within 100 nanoseconds. And so there's like an anomalously high number of inter-arrival rates which are happening at within 100 nanoseconds. It's between, I don't think I mentioned it here. Oh yeah, I implied it over here by having 85 nanoseconds over here. That's the experimentally, that's the empirical downtime that we decided on. So between 85 nanoseconds and 100 nanoseconds, we found that there was an anomalously high number of inter-arrival rates. It was high enough that if you try to do an ML fit for an exponential, including those values, it would skew the parameter like really heavily. So the, like, if you know the exponential, for an exponential, the average waiting time should be the same as the standard deviation, but it wasn't. And we hypothesized that this anomaly might be a result of sub-Poissonian light statistics, or what's called squeezed light, but I don't know much about that, so I can't conclude anything about that. So there's that. We have some experimental key rates. So over here we say this anomaly may manifest as brief periods of time where P appears to be higher than it should be. So before we saw, if we saw D, when P is small, H sub ratio is pretty much going to be 1. And that makes sense, because the fewer occupied bins there are, the less chance there is for an occupied bin to affect another occupied bin. So maybe in the small values of P that we usually work with, downtime isn't going to be much of a problem at all. But maybe there's like, just maybe there's like brief periods of time where P appears to be higher than it should be, and this might result in something like this. So this is also a plot that I generated from the experimental data. So we have various values of frame size, but we're varying along the x-axis, we're varying the bin size. And it's in microseconds, so you can see over here, if it's 0.1, you have, that's going to be 100 nanoseconds. So below 100 nanoseconds, you can see that after this initial local maximum to the right, we have this sudden spike. That suddenly the rate, it suddenly appears to go up. And there's a possibility that this may be the same thing as what we were seeing before, where it looks like the key rate was being maximized, but actually the entropy of the bits that we're getting isn't really that high. So in further research, this is something we could test by, I believe, I don't know if Nick mentioned this in his thesis defense, but he helped. He was using the NIST statistical testing suite in order to take a look at the randomness of some of these bit sequences. So if we used that to actually take a look at the bit sequences that we get over here, we could see if it really is, if it's still random. And then here we can take, there are also, so until now we were talking about so this is what you were asking, I think you were asking about, Anand, with the values of D greater than N. So we were talking about integer values of D where D is less than N so far. But then what happens when we have non-integer downtime, which is probably what's going to be the case in a practical system, in a real life situation? And then what happens if the downtime D is greater than N? Well, for these formulas, I got just by playing around with some of these plots and then just looking at them. And so these seem, at least for the parameters that I played around with, this seems to fit for the most part. That if you have a non-integer downtime, you can just linearly interpolate between the closest, between the nearest integer values of D. So hopefully I got this linear interpolation formula correct. And then for downtime D greater than N, it appears that the rate you end up getting is going to be the rate that you get with downtime N minus 1, but scaled by some factor. So that's going to be N over D plus 1 and in units of bits per bin. And then here's a little bit about the question I asked, like in the abstract, which is how does time entanglement do versus polarization entanglement? And we can see here as downtime increases, it seems that so the blue line over here, the blue curve is supposed to represent R sub p when you do consider downtime. And I did that just by finding the minimum of that value by 1 over D. So that's what the blue curve is. So you can see that it does drop down, and the red curve, which is R sub TOA, the upper bound for R sub TOA when considering non-zero downtime, that does also go down, but the rate for the polarization entanglement appears to go down faster. So for now, it seems like it may be that time entanglement really is just better than polarization entanglement in general. And now we go into other sources of error. This includes jitter, and here are some of the ways that Nick and I attempted to address this jitter. So here I suggested this simple code where you just have this matrix here, and this is something you apply to the frame before you apply it to the binning scheme. So you would have this. So so once you have a valid one-hot encoding, you would theoretically just get one of these columns out as the syndrome bits, and then you would share that over a public channel. And then based on this, you can correct the jitters of from one bin to another bin. Nick, on the other hand, had a little more sophisticated code. I don't know if he mentioned this, but he came up with this, which is that you do apply the binning scheme, or at least something like PPM, where the jitters of one change the value of the output bit by 1. And so because of that, you apply gray coding to the output of the frame according to the binning scheme. And then because of that, and because of how gray coding works, now jitters of 1 are going to end up just changing 1 bit in this gray code. And so these can be fixed easily by an LDPC code. And then if you want, you can undo the gray coding. And then here are some basic results that we got by testing these codes. It seems that the amount of error that you get from jitters of one bin to the adjacent bins is so high that if you correct them, the shared bit rate is actually it actually goes up, despite the fact that you're now losing some bits because of the reconciliation. But then past that point, it does generally just go down. And that might be because what seems like jitter greater than one bin apart, it might not actually be jitter, but just the result of things like dark counts and absorptions. And that's pretty much it. Yeah. Just to have a quick review of what we went over, we had the system model. We explained why we use QKD and why we use QKD time entanglement, and then introduced the idea of bit extraction schemes. And then we explained recovery time or downtime, how that affects our key rate, and then how we can calculate these effects. And then I showed a little bit of this online tool that I made, and which uses these methods that I introduced. And then we have some other things that we could, that I or other people continuing this research could look further into. So that's the end. Are there any questions?